a what we call selectively permeable membrane. What it makes the selective permeability for simple diffusion would be those teeny tiny spaces between phospholipids. Okay? See if I can get all of this on here. So, small, very, very small substances. And polarity, this is where your chemistry comes in. Polarity is important. Remember that the phospholipid heads are polar and the tails are nonpolar. So this is through spaces between the phospholipids. Lipids. And finally, oh, no, not finally. So, no energy. That's because it goes from higher to lower concentration. I'm going to abbreviate concentration, everyone. Okay? So that's simple diffusion. It requires no energy. Something very small is moving between the spaces, between the phospholipids, and that's a selectively permeable membrane. Facilitated diffusion. Movement across a selectively membrane. Larger and through protein channels. They're like gates in the cell membrane. Okay? Whoops. Larger. Wait, let me move this. Larger, and then put this here. Through protein channels. This is not the only place we see protein channels. We see them in active transport, and no energy because it's higher to lower concentration. That's the movement direction. So as long as we're moving from higher to lower, we don't need any energy. It's more like watching a big boulder roll down a hill instead of pushing a boulder up a hill. That would be more like active transport. So I'm going to go in and put active transport because I have more to say about osmosis. Active transport. This is movement across a selectively permeable membrane, and multiple sizes. So it can be really small materials, like even hydrogen ions, or something bigger. Okay, this is also through protein channels, even if it's small. And here's where it's really different. Energy required. And if you want to guess why, I'll give you a second. And then I'll write, because it's lower to higher concentration. So the direction is different. So it actually, whatever it is, has to be pumped. And to pump something, that takes energy. The energy is in the form of ATP. ATP is adenosine triphosphate. We're going to talk a lot more about ATP. I think it's next week when we start energy. So I don't want to spend too much time on that right now. Then there's osmosis. And I have more to say about accident. Movement across a selectively permeable membrane. And this is specifically water that's moving. And it goes through the spaces between the phospholipids. I wish I had my big boards like I do in the classroom. And that I didn't have to worry about falling down on me. And no energy. And I want to put something right here, this asterisk, because I'm going to talk about it just a little bit more after I erase the board. Okay? So in a way it's like simple diffusion, except that it's specifically the movement of water. Okay. Starting to try to fall. So, tonicity relates to osmosis. And the movement of the water is dependent on the solute concentrations outside and inside the cell. Okay, so what I'm going to do is I'm going to draw 3 beakers. And in these beakers there are solutions. One of these is hypotonic, one is isotonic, and one is hypertonic. Inside, I am going to put a red blood cell. Now this is not realistic, we wouldn't have a single red blood cell, but I want to show you what we're talking about. Inside the red blood cell we have, what is it, 0.0, I should have looked this up. We have 0.85% or 0.05. Sodium chloride. It's the same for all of them. This is how your red blood cells are. Now this works for other types of cells, but I'm just using this as an example. So we know what the solute concentration is inside the red blood cell of salt, sodium chloride. In a hypotonic solution, we might have 0% sodium chloride. And while that isn't a lot, that is less. Okay? So what happens is, because of just chemical properties, or a chemical property to achieve an equilibrium, is that water moves, there's a net movement of water into the cell to dilute this so it's the same as what's outside. No energy involved. So what we have is a net movement inside of water. Okay? A little bit outside, but mostly inside. So what happens to a red blood cell in a hypotonic solution is it swells. It swells, in fact, it can swell to the point of bursting. This is why you would never put distilled water in somebody's IV. You'd kill them because their red blood cells would burst because water would move into the red blood cells from the fluid you're putting into the IV. Instead, IVs contain isotonic saline and other fluids or other materials, other compounds, but But they have to be, the fluid in an IV has to be isotonic. What you put in your eyes, what you use for your contacts, that's all isotonic. In fact, if you look on the label, it'll say isotonic saline, most likely. And here, it's the same. So, over here, well, no, I'll come back to that. So basically, water molecules move in, but water molecules move out. Because they do that, but there's no net movement of water into or out of the cell. This one, there's a net movement of water into the cell. So what about a hypertonic? Hyper or more. So the solution that's outside of the cell might be 2% sodium chloride. So that's more. Hey, do you want to guess which direction there'll be a net movement of water? Well, let's see. That one was into the cell. This one is, there's no net movement, so it must be out. So yes, the sodium chloride concentration is greater outside of the cell, so the water molecules move out again to achieve that equilibrium, to dilute now the solution outside of the cell, to dilute the sodium chloride there. And so we have a net movement out of the cell. This is not good for red blood cells or other cells either, because this will cause them to shrivel up as the water moves out. If we were doing our face-to-face lab, we would have a lab where we look at de-shelled chicken eggs. Because what's cool about those is they're big enough that we can weigh them. And we put a couple of eggs in a hypotonic solution, one in a close to isotonic, and others in a hypertonic solution. And basically, what we would see over time is these eggs would gain weight because they take in water. Any that are close to isotonic would not have much change in the weight. And in hypertonic, those eggs lose weight because they're losing water. It's a great lab. Unfortunately, we can't do that. Okay, so that's the end of part 1 of the lecture.